Good afternoon, everybody. Welcome to lecture. I want to let you know that I have the exams graded and I returned them last time, but if you weren't here, I still have your exam. I just forgot to bring it to lecture today, so I will for sure bring it on Friday. If you want to get it sooner, you can stop by my office and that'll work out fine. So what I have for you today to start things off is a molecule of the day. So there's going to be just like 2 or 3 of these, probably 3 of these molecules on exam 4. These are new ones. None of the old molecules of the day will be on the exam, but these new ones will. Here is a molecule of the day. This is amoxicillin. This is an antibiotic drug used to treat bacterial infections. It is the first choice for ear infections, I have found in my experience. I have a couple kids that had a lot of ear infections, and usually the first thing they do is give amoxicillin, and if that doesn't work, there's some others that they supply or provide or recommend or prescribe, I should say. But yeah, it's a real commonly used antibiotic. The reason I've got it up here today is it has some structural features that we're going to talk about, functional groups that are the topic of the next chapter that we're going to tackle. It has a carboxylic acid in it. You'll get on this side so we can see it more clearly from the camera's angle. Carboxylic acid. There is a amide right here. Okay, then there is this amide right here. This is a nitrogen bound to a carbonyl, but it's in a ring. And this is a special kind of amide that we're going to learn to call a lactam. And the thing about this antibiotic type is it's a special type called a beta-lactam because it has this functional group in it. The beta-lactam is the 4-membered ring that contains an amide within it, and that is the key to how these molecules work. They exhibit their antibacterial properties. They fit into an enzyme that is responsible for creating the cell wall that the bacteria need to live, and they basically mess up that enzyme. And there's a lot of them that have the same sort of structural features. This is a member of the penicillin class, so penicillin is got the same structure. There's a class called the cephalosporins, which are really similar. They have a different ring over here, but a beta-lactam in them. And then there's a lot of structural variation on this left half of the molecule that gives them unique properties and either helps avoid resistance or confers some subtle change in the clinical efficacy. But anyway, this beta-lactam theme is really important. And so this is one that we're going to talk about, a functional group. We're going to deal with carboxylic acids and their derivatives in this next chapter that we're looking at. So there's a molecule of the day for you. Let's talk about the survey question. There was a survey question and it dealt with aldol reaction. And so what I'm going to do is draw the survey question and just work through the answer. So you were given a structure like this and asked to predict what would the starting aldehyde or ketone need to be in order to make this. And then there were a bunch of options you could select from, an A, B, C, D, E kind of thing. So what we talked about last time when we were talking about aldol is that you want to look for the carbonyl group, and then if this is one that's got a double bond here like this is the alpha position and that's the beta position. And the bond that happened or was made to bring them together happens between this carbon and that carbon. The alpha position of the enolate attacks the carbonyl carbon of the aldehyde or ketone. And so the beta carbon used to be a carbonyl group. And so it reacts, you get an aldol product, and then it dehydrates to give this alpha beta unsaturated product where there's a double bond here. So if you just think about what this would come from, it comes from a single ketone that's got this structure. And so I'll draw both pieces. It's the same ketone I'm drawing twice here, but I'm going to draw it in a way such that you can hopefully see where the parts come together. So this carbon right here that I've labeled beta, that was the carbonyl group over here. So you just had to draw it once, select it from the list, but that's the answer. There was a lot of carbonyl containing molecules that look maybe kind of like they might be right, but only this one is actually right. So any questions about the survey? Hopefully that one was easy. I haven't had a chance to look at the statistics yet, but I'm hoping everybody did well. Okay. So on to some new stuff then. The last new content that we're going to talk about in the course has to do with classes of molecules called carboxylic acids and their derivatives. So we've talked about a little bit about all of these molecules before. And this is chapter 20 in the textbook. It's called carboxylic acids and their derivatives. So what's a carboxylic acid derivative anyway? We've talked about carboxylic acids before. Chapter 19 was all about carboxylic acids, but we're going to talk about them now. So let's just get you oriented to what these things are. We'll go through some examples of each member of the class, and then we'll talk about some, not really nomenclature, not proper nomenclature, not like really intense nomenclature, but sort of kind of nomenclature light on these things. So first of all, there is the carboxylic acid, which is the kind of like the parent of the class. Carboxylic acid. And all of the members of the class are related to carboxylic acid. And carboxylic acid has an OH group here. And what you'll see about the derivatives is the derivatives are all very similar to carboxylic acid. They just have a different group in place of the OH. So in the list of carboxylic acid derivatives, then, these are all things that are related to carboxylic acids. The ones we're going to talk about are one that looks like this, which is called amide. We saw two amide structures within the amoxicillin molecule of the day. It's got a carbonyl that's attached to a nitrogen. And the nitrogen can be bound to hydrogens or carbon groups, and they're all amides. So that's why I'm leaving these bonds like unlabeled. They could be carbon groups, they could be hydrogens, but it's all amides. Then another member of the class is ester. So esters look like this. And what is similar about all these things, just to highlight what distinguishes them and what relates them, it's the group that's attached to the carbonyl in each case. So that's the thing that's changing as the functional group changes. Ester has an OR group, and I put OR prime here just to indicate that that R group could be different than that R group. Could also be the same, but it doesn't have to be the same. And then there is another variant on these structures that looks like this. I'm running out of space here, so I'm going to have to get kind of strategic with my drawing. But there is a molecule that has a different group. It's got an O carbonyl R. These are called anhydrides. And then finally, the last member of the class is one that we've seen before and worked with actually in Friedel-Crafts acylation reactions, acid chloride. So acid chlorides have a chloride in place of the other group. So this is called acid chloride. And there's a hierarchy of reactivity. The acid chloride is the most reactive. And then down here on this end, amide is least reactive. And they're arranged in the order that I'm showing here. So amide is least reactive, ester is more reactive, anhydride is more reactive, and acid chloride is even more reactive, the most reactive. And carboxylic acids fit in somewhere near esters, but it's kind of complicated with carboxylic acids because they not only have this group that, that I've highlighted in orange, but they also have an acidic proton. So their chemistry is a little bit more complicated, but consider them to be kind of like the parent. All of these derivatives are related to carboxylic acid, and carboxylic acid is related to all of them. So those are the basic functional groups that we're going to talk about in this chapter. And we're going to discuss some of their reactivities, how to make them, and how they react. So what I thought I would do first is talk about just sort of some things to like orient you towards these functional groups, because there's a few like little things that it's good to know about to classify them a little bit more specifically. So we're going to talk about that next, especially with some of these that you're not all that familiar with, like anhydrides. We haven't really done a whole lot with anhydrides. We had a reaction in the lab where we used one in a Diels-Alder reaction, but I'm going to tell you just a little bit about each one of these classes. So anhydrides, we'll start off with that one. There are different kinds of anhydrides. You can have an anhydride where the two R groups are the same as each other. So like, for example, here's one where the two groups on either side of the carbonyl are the same. So this is sometimes called a symmetrical anhydride. This particular one is called acetic anhydride. This is an example of a symmetrical anhydride. I'll just tell you straight out, it's called acetic anhydride. It's the most important anhydride. It's the one that gets used the most. Basically, it's a really useful reactive species for doing lots of different things. But symmetrical anhydride is one way that you can see an anhydride. You can also have anhydrides that are not symmetrical. So in other words, they have different R groups, not two that are the same, but one that is different. So for example, here's a example of an anhydride that's not symmetrical. So these are sometimes called mixed anhydrides. You could also call them non-symmetric or unsymmetric anhydrides. But a mixed anhydride has just different R groups. So it's got one methyl group and then a hydrogen over here. So the thing about these is that they have two carbonyls, and both of these carbonyls are partially positive. So they're both potentially reactive with nucleophiles, but sometimes one is more reactive than the other. So in cases like that, you have to decide which of the two carbonyls is going to be more likely to be attacked by a nucleophile. So we'll just maybe talk about this little detail right now. Between the two, when we were looking at aldehydes and ketones, like if you imagine this middle part isn't there, we talked about the reactivity of aldehydes and ketones last chapter. We said that there's two things that make them reactive with nucleophiles. It's like how big is the partial positive charge, and then how bulky is the area around them. So if you're a nucleophile trying to attack a partial positive charge, you've got a lot of negative charge. You want to come in and attack this positive charge. So the bigger the partial positive charge, the more you're attracted to it. So the more reactive it would be. The methyl group has a donating effect, makes that partial positive charge a little smaller. So in this case, this is got a bigger partial positive charge. So I'll try to qualitatively show this by drawing the partial positive a bit bigger. I don't know if that's really it's not an official way to do like nomenclature, but it gets the idea across that that carbonyl carbon is more partially positive. So a nucleophile is going to be more attracted to it. The other thing is steric hindrance. So you've got over here a hydrogen, which is a small group, and then over here you've got a methyl, which is a much larger group. So that is the more reactive carbonyl for two reasons. It's more electron poor, which makes it more reactive, and it's also less bulky in the neighborhood of the carbonyl. So so the more reactive C double bond O is here. I'll just put a label there just to indicate that that's the one that if you put a nucleophile in, that's the one the nucleophile is going to want to go and attack. So we'll get to talking about anhydride chemistry specifically in a little bit, but that's just a bit of a heads up to start thinking about. You can have cyclic anhydrides as well. So I'll draw an example of this. It's one of the ones that we used in our lab experiment. This is an example of a cyclic anhydride. This was maleic anhydride that we used this double bond as a dienophile in a Diels-Alder reaction. This chapter, we're going to be specifically thinking about the carbonyl groups. And again, the thing about them is they have partial positive charge, and so nucleophiles will want to go and attack there. So those are some anhydrides. Any questions about anhydrides so far? So at this point, it's just getting used to recognizing the functional group, and when you see it, to know that that's an anhydride and that it has a particular place in the reactivity hierarchy, which is, according to this list over here, pretty high up. So these are pretty reactive species. If you see one of these in a molecule, you can bet that that's going to be a hot spot where a reaction is likely to happen. All right, let's talk about esters next. So we did anhydrides. Acid chlorides are one that we've seen before, and there's not a lot of structural variation in them. So they're not quite as complicated, so that's why I'm not really talking about them. We'll talk about the reactivity, which is really interesting in a little bit. But anhydrides needed a little bit of discussion. Esters do too, so we're going to talk a little bit about esters next. Then we'll go on and we'll talk about amides. So esters can be acyclic. In other words, they're not in a ring. As an example of that, here is an example of a non-cyclic ester. So this is let's call it a non-cyclic ester. It's kind of an ordinary ester. This particular one happens to be a molecule called isopentyl acetate, and it smells like bananas. So and it's the molecule in bananas that make bananas smell distinctly like a banana. So they sometimes smell good. Sometimes they're found in a lot of different fruits. And the thing is it's got this carbonyl group and then the OR group. So this is the part that makes it different than an anhydride or a carboxylic acid or an amide or an acid chloride. But you can have amides, esters wrapped up into rings as well. So I'm going to put one of those up there as well. So here's an example of an ester that is within a ring. This is a cyclic ester, and they have special names. This is called a lactone. And that's just the name that we give to esters that are cyclic. And you can classify them a little bit more specifically by their ring size. Like, in other words, how big is the ring that contains the ester? It's got to be the ring that contains the OR group and is attached to the carbonyl. So the way that people do this is they give them Greek letter labels, the carbons. You look at the carbonyl carbon, and then you say the carbon next to it's the alpha position. So we did that when we were talking about carbonyl chemistry with aldol condensations. We labeled the position that was next to the carbonyl with an alpha. Then you just need to know a little bit of the Greek alphabet. So you go alpha, beta, gamma, and delta. So the O that is part of this amide is attached at the delta position. So this would be called a delta lactone. And you can have esters that have smaller or larger rings. 6-membered ring is one of the most common ones. The other one that's really common is a 5-membered ring, just because these are ones that have very low ring strain. So you see these a lot. This is an example of, and I'll put a methyl group on here just to make sure that we've got a little bit of variety. When you're trying to classify this one, it's a lactone, and here's the alpha position, here's the beta position, here's the gamma position, and so this is the O here is attached to the gamma position, so this is a gamma lactone. Maybe what I'll do is I'll spell it out, just because I don't want anybody to be confused by my drawing of the gamma symbol, because I don't know, it's not a symbol you often see, so it might look like a squiggle if you're not sort of tuned into it. But there's lots of interesting lactones out there, lots of important natural products. Pharmaceuticals contain cyclic esters. Sometimes they're in small rings like this, sometimes they're in really big rings. Like, I was thinking, one of the molecules of the day I was thinking of bringing was erythromycin, which is another antibiotic, completely different class, very different, but that one has a cyclic ester in it. So, so there's lots of good, important examples of lactones out there. Any questions about esters? Cyclic, acyclic? All right, just kind of getting you familiar with the classes here. And then, oh, I should probably not erase this yet. I want to flash over here and just talk about the next carboxylic acid. I'll put this back. There we go. Let's talk about amides now. So we've got a discussion of anhydrides, esters, and amides. And we'll go through a similar kind of analysis of amides. We'll talk about acyclic amides, and we'll talk about cyclic amides, and do some classification. So next up on the discussion list is amide. Amides. Sometimes you get little differences in pronunciations with these. So if you hear somebody call it an amide, that's the same thing. Amide, amide. It's like tomato and tomato, and there isn't really one right way to pronounce it. So, but these are molecules that contain a carbonyl with an R group and a nitrogen. And there are different ways to do this. So if you have an amide like this, and if you look at the nitrogen and count the number of carbon groups that are attached, this nitrogen has one carbon group attached, the carbonyl. This is what's called a primary amide, because it has just that one carbon group attached. There are amides out there that have two carbon groups, where these R groups are carbons, carbon-containing groups, and so this is called a secondary amide. And these are really important because there are a lot of proteins. Most proteins have amide bonds that hold them together, that hold all the residues together, and most often they're secondary amides. Not always, but very often. And then there's a final way you can have an amide where there are two R groups, or I should say, if you count the nitrogen, there's three R groups on the nitrogen, the carbonyl, and two additional potentially different R groups. So this is, as you might imagine, having three carbon groups, a tertiary amide. And so those are all just general classes of amides. Okay, cyclic amides. You can have cyclic amides too, like we saw with the molecule of the day, a cyclic amide, an amide that was in a four-membered ring. Those are called lactams. So we're going to talk about cyclic amides next. Cyclic amides are called lactams. And it's a bit unfortunate that the first part of the name sounds pretty much the same as lactone and lactam, Very similar. The way I remember it, if you're struggling here, lactone, there's an O in the name, so I think O, that's what an ester has. For lactam, there's an am in it, which is kind of, for me, invokes amine, nitrogen. So I don't know, whatever mechanism, mnemonic device you want to use, but when you see lactam, think cyclic amide. So these are molecules that contain an amide bond that's in a ring. And so just to define like that class that we talked about before, here's a cyclic amide, a lactam that's got, if you classify the positions, the beta position is where the nitrogen is attached. So this is called a beta lactam. And these are pretty reactive, which makes them really good at their therapeutic job of basically destroying an enzyme that's important for the life of a bacteria. So they like to pop open. But there are other kinds of lactams as well. So you can have lactams that are parts of 5-membered rings. These are a lot more stable. Like for example, this one, if you count by letters the various positions on this one, this is a gamma lactone. And you can get delta lactones, and there's there's a huge variety, but most of the time 5 and 6-membered rings are the most common. Yes, there's a question. Sorry, yes. So the question is don't I have this wrong? And you're right. Yes, thank you for correcting me. Lactam, yep. Mm-hmm. Good catch. All right. The pattern is what you need to know. So if you saw like some lactam or lactone out there, you could tell people, hey, that's a delta lactone, or that's a beta lactam, or whatever. Just that's the kind of level of nomenclature that I'm hoping you can like absorb. All right, that's an introduction. Any questions about this stuff so far? Okay, well, let's move on to reactivity. We talked about how acid chlorides are the most reactive and amides are the least reactive, but why? That's what we're going to address here. So when you have amide, ester, anhydride, and acid chloride, and the reactivity is like this: most reactive, least reactive. The reason that they are this way has to do with the difference being a reflection of their leaving group ability. The thing that's different about these guys is this bit. Like, what is the piece that's attached to the carbonyl that could potentially leave? And the reason that they are the way they are, like that this is least reactive, is because nitrogen's a very poor leaving group. It leaves as a very strong base. So this is the worst leaving group. When it leaves, it's a very strong base. If you look at in the pKa table, the pKa of like NH3, it's 38, which is a very, very weak acid, which means that nitrogen minus is a very strong base. You go over here, and if we go to the other end, you get Cl, which is a very good leaving group. And the reason for that is it's, I'm just going to say Cl minus is a very weak base. So it's really easy for a nucleophile to come in and attack here and bump out the chloride, because chloride is almost always a weaker base than the nucleophile that you use to attack. So to get reactions to work, they need to go from stronger base to weaker base, for example. So if you've got a nucleophile, and the nucleophile is a pretty strong nucleophile, it's a pretty strong base, and then it attacks an acid chloride and it kicks out a Cl minus, it goes from strong base to weak base. That's a really good situation. That's a reaction that really is going to work. If you're trying to bump out a nitrogen as an N minus, that's really hard because you're trying to make a really strong base. And N minus here in this situation, if it were like this, it'd be nitrogen with a couple of lone pairs and a minus charge. That's a really, really strong base, a very poor leaving group. So, you know, it's really tough to do this one. So these tend to not be very reactive, more reactive, more reactive, and more reactive. And there's some trends that you can develop around this. And so I'm going to give you a kind of a guideline, set of guidelines here to to use to help you predict what kinds of reactions are possible and which ones aren't. If you can remember the hierarchy of reactivity and the difference in base strength of the leaving group, this then will all make sense, hopefully. In general, it is easy to convert a more reactive carboxylic acid derivative into a less reactive one. To a less reactive derivative. So let's just take a look at this list again and point out some reactions that you would predict would be easy based on this rule. So if you have yourself an acid chloride, that's the most reactive derivative, you can make that into anything else. You can make that into an anhydride, you can make it into an ester, you can make it into an amide. You can also make it into a carboxylic acid. If you have an anhydride, that's a quite reactive group, but it's not as reactive as this. So you can turn your anhydride into an ester or an amide, but you can't turn it into an acid chloride because that's going the wrong way energetically, going from a less reactive to a more reactive. It's always got to go downhill. If you've got an ester, you can't make an anhydride or an acid chloride out of it, but you can make an amide out of it. And if you have an amide, you can't make any of those other things out of it. So amides are the least reactive. This is where things kind of tend to roll down to this low energy point. And that's one of the rules that I want to share with you. The other thing I want to share with you is that they're all related, these derivatives, these four derivatives, they're all related to carboxylic acids. All the derivatives, that's amide, ester, anhydride, and acid chloride, these four derivatives can be synthesized from carboxylic acids and converted into carboxylic acids. So that's why I said the carboxylic acid is kind of like the parent functional group. So if you have any one of the derivatives, it could be made from a carboxylic acid, could be converted into a carboxylic acid. So let's just take a look at this table of derivatives over here, this list, and talk about it. So if you wanted an acid chloride, you could get one from a carboxylic acid. There are reactions that will do that. If you want an anhydride, you can make those from carboxylic acids. It's a little bit complicated. This reaction doesn't work all that well, but it's at least theoretically possible. Esters can be very easily made from carboxylic acids, and amides can be made from carboxylic acids really easily. These can all be converted into carboxylic acids by adding water and sometimes a catalyst or something. So basically, you can replace any one of these orange highlighted groups with an OH just by treating it with water and sometimes a catalyst. So that's how this whole family kind of behaves. And so what we're going to do next is talk about their reactions. So we're going to talk about, like, what are the reactions of acid chlorides? What are the reactions of anhydrides? What about esters? What about amides? And just go through it and talk about, it's the interconversion reactions that we're going to talk about. Converting acid chloride into these other functional groups, or acid chloride into carboxylic acid. So it's going to be a lot of the same kind of mechanism over and over again. So there's a bunch of molecules up here, and we're going to look at a lot of reactions, but they're all really very similar. So as long as you understand the hierarchy of reactivity, then I think it becomes a lot easier. So that's what I hope anyway. So let's start off with the most reactive of the bunch. We're going to talk about the acid chlorides first. Like, what do these do? How can these be useful? And they'll react into any of these others or carboxylic acid. They're very useful for synthesis. They're very reactive. These things, they're kind of notorious to keep around. Like, I have some of these on the shelf. They start to eat through their bottle cap eventually. I mean, they're just trying to get out. And they're really reactive. Whereas, like, the esters and the amides, they'll sit there kind of, calmly on the shelf for, indefinitely. So there's a big difference in how these things behave. And acid chlorides are kind of the most exciting of the bunch. So we'll start with those. So acid chlorides, we'll talk a little bit about them in general. So this is going to be reactions of acid chlorides. I don't like that piece of chalk. That piece of chalk is too hard. If you use a chalk that's too hard, it's hard to erase then. So I can just tell. I'm just like, that's not going to work. Okay, reactions of acid chlorides. So I'm going to give you a couple of bullet points to start things off, just to put it in perspective. These are the most reactive. Derivative of carboxylic acid. And can be converted into anything. Converted into any other derivative or carboxylic acid. They react with both strong and weak nucleophiles. Without any catalyst needed. So they really want to react. You put them in with any kind of nucleophile, they'll react with it. And we're going to look at examples with strong nucleophiles and with weak nucleophiles, just so you can get a sense of how that works. And we'll go through these mechanisms too. And after a while, hopefully it becomes almost like second nature. Looking at these reactions, you can figure out what's going to happen. So here's a reaction to make an anhydride. Here's how you can convert an acid chloride into an anhydride. Here's an acid chloride. If you want to make an anhydride, you need some kind of a nucleophile that brings the other piece. So I will take a look at, for example, a carboxylic acid. And for my carboxylic acid, I'll use one that looks just a little different. It's got an ethyl group here on the carbonyl, whereas this one has a methyl. And yeah, let's figure out what happens here. So we've got a partially positive carbon that's a very strongly partially positive carbon because it's got the carbonyl that's oxygen tugging on electrons, and it's also got a chlorine that's pulling electrons away from it really intensely. So big partial positive charge there. These two atoms both have really partial negative charge. So either one of them you could formulate as coming in and attacking. So I'm going to show just lone pair here coming and making a bond there and pushing electron pair up onto oxygen. So this will give an O minus. There'll be a Cl minus that's still attached, a C that's still attached. There's an OH here that came along with the nucleophile piece, and a formal plus charge on that oxygen. So this is an addition reaction. The weak nucleophile is adding to the carbonyl of the acid chloride. And now we've got a couple of different leaving groups. We've got this thing that we just added could leave, and that would be like the reverse of this reaction. So oxygen lone pair can swing down and reform the carbonyl and kick out a leaving group. And it could either be this that's the leaving group, or it could be the Cl minus. So I'm going to show it pushing out the Cl minus. This is an elimination reaction. Elimination reaction. And when this happens, you get the two carbonyls of the anhydride. And there's still an H attached here, and there's still a formal positive charge here. And we have a Cl minus as well. That was the leaving group on the acid chloride. So the last thing that happens is that Cl minus comes by and grabs a proton, and you get the finished anhydride. All the oxygens are neutral. There's a methyl group over on the left side, an ethyl group on the right side, and the other product is HCl. So the reaction generates some HCl. You'd actually see this probably fuming off the reaction when you're doing it. It would end up probably protonating the product, but that's the anhydride product right there. Put a title up here. Converting acid chloride into anhydride. which is the next most reactive derivative. Okay, and then we'll talk about the one that's lower down, so taking an acid chloride, making it into an ester. This is converting acid chloride into ester. And one of the things that's a little different about this one is that oftentimes a weak base is added. A weak base is often added. You don't necessarily have to add one, but it's often added to neutralize HCl. So one of the things you noticed about this reaction is that it produced, if I go over here back to this previous reaction scheme, is that when it was all done, you get HCl. And you know, that is a really strong acid. And that might be okay, but if you've got an acid-sensitive molecule and you don't want a lot of this produced, you can solve that problem by adding a weak base to mop this up, basically. And so that's what we're going to see in this next reaction here. We're going to see formation of an ester in the presence of a weak base to try to mitigate that strong acid, making the whole reaction really acidic. Okay, so let's talk about acid chloride reacting with an alcohol in the presence of a weak base. So for this one, I'm going to use this alcohol, just propyl alcohol, just for I don't know, something that's different than methyl. And the other reagent I'm going to put in here is one called pyridine. So this is one of the things that the book talks about, is this is pyridine, and it is a weak base. So its function is that that lone pair likes to grab H's. So the final product, when this is all done, I'll show you the product and then we'll go through the mechanism, is you get an ester, and you also get the pyridine having grabbed a proton, and it becomes this salt species. It's called pyridinium chloride. But essentially, if you keep track of what happened, HCl is here, but it's not in its HCl form. There's an H there and a Cl there. So this is not a real strong acid. Like HCl by itself, very strong acid. This molecule, not nearly as acidic, so much milder. So this is a way of avoiding really strong acid conditions forming. So let's talk about how this works mechanistically, where the pyridine comes into play and how it does its job, and how you end up with an ester, because that's really the point of it. Just make an ester. And if we're talking about esters, we could talk about one that's kind of a little bit more interesting. We can talk about that banana oil type one. In case you ever want to synthesize some banana oil. If you want to go into the flavors and fragrances industry, you're going to have to get good at synthesizing esters. There's a bunch of different ways to do that, but let's talk about that. So here's a reaction that uses this acid chloride and this alcohol and pyridine. So, mechanism. It starts off with the oxygen of the alcohol attacking the carbonyl carbon. So here it goes. Just like that. Yeah, I don't know what that's trying to tell me something. So tax the carbonyl carbon and electrons get pushed up onto the oxygen. This is kind of like how almost all of these reactions start. Something attacks the carbonyl. Not always, but with acid chlorides, that's how it starts. Okay, and so that's an addition reaction, and we get as an intermediate this species where there's an O- up here. The chlorine is still attached, but now we have this alcohol species that has been added. It's got a formal positive charge. There's one lone pair left, like that. And that is the very first thing. And the next thing that happens is that pyridine comes by and grabs this proton. So pyridine is a weak base. It likes to grab protons like this. And then you get a species that looks like this, where there's an O- up here, like there was before. That part hasn't changed. But now we have the Cl here. And now it's just the neutral alcohol species that's there. And the other product that we have is the pyridine has accepted that proton and has become protonated. Pyridinium chloride. By the way, this is an aromatic ring. Just a little flashback to one of the previous chapters. Is that ring aromatic? Yes? No? Well, let's see. It's still a ring. It's got 2, 4, 6 pi electrons. It's still aromatic. So this base, pyridine acting as a base didn't impact its aromaticity, which is why it works. If it was going to make this ring non-aromatic, then it would not be a very good base at all. It'd be a very poor base. So, okay. So what happens next then is that the leaving group leaves. So this lone pair of electrons swings down and then something gets pushed out. And here's the difference. Kicking out an oxygen to give an O-, that's a really quite strong base. Kicking out a Cl-, that's a really weak base. So this is the way it wants to work. And this reaction then gives the finished ester. And there's a Cl-. Actually, what I should have done here is not included the Cl- yet, because at this point, that minus and that cation are the salt pair. Then once the leaving group is ejected, the chloride comes off, then it's Cl- that pairs with this. So this is the finished ester right here. So you'll see a bunch of these kinds of mechanisms in probably in the homework sets to try to figure out. All right, let's talk about then I'll just set up the next topic. We're probably not going to get through it, but I'll tell you about amide synthesis from acid chlorides. That's one of the last ones we're going to talk about. So the way I've been describing this is acid chloride converted into amide. So in order to do this, you'll have an acid chloride and you'll have some sort of an amine that you'll go in with, and this amine could have many different things on it. It's got to have at least one H in order for this to really work well. So I'll just say here's an example of an amine that would work. And here's the thing about amide synthesis from acid chlorides. You need to have 2 equivalents of the amine. Needed in order for you to get a good yield. And we'll talk about mechanistically why that is, but here's a hint. If you look at the products that come out of this. There is the amide, which was the point of doing the reaction. But then the other product is you get the protonated amine. And a Cl minus. So one amine acts as nucleophile. The other acts as a base. And so we'll get into that next time. So that is formation of an amide from an acid chloride using 2 equivalents of an amine. All right. When we come back next time, we'll talk more about, finish up acid chlorides, talk about anhydrides, and then get into probably carboxylic acids, because they're really interesting too. Have a good day. See you on Friday.